So there are some consequences to that. The most polar covalent bonds in Bio 111 are the following. Anything, we don't really care what it is, to oxygen, H. That bond is delta minus delta plus. That OH bond right here is very polar. And likewise, if we have nitrogen, and we don't really care what else is bonded to it, X and Y, basically whatever, this NH bond is also very polar. And that's likewise delta plus and delta minus, right? Because nitrogen is very electronegative, right? So likewise with oxygen, when oxygen and hydrogen try to share electrons, it's a very unequal sharing, and when nitrogen and hydrogen share electrons, it's a very unequal sharing. And those bonds are very polar, right? And it all comes down to unlike charges attract. And so there's a neat feature. If you have these, you can form a certain kind of non-covalent bond that's really important in biology. That leads to hydrogen bonds. We call them H bonds for short, and they're weaker than covalent. They are non-covalent bonds, and they're weaker than covalent bonds. And they're all, just like all other bonds, they're based on, unlike partial, in this case, charges attract. It's always plus and minus attract each other. So it turns out, if you have water, which is a classic example, and it's got its lone pairs, let me get up a little more space. This is delta plus, slightly positive, and the oxygen is slightly negative. And if you have another water molecule sitting over here, lined up like this, this is delta plus and delta minus. And the unlike partial charges can attract. Let me do this in a slightly different color. Put something in blue maybe. And you form what's called here a hydrogen bond. Okay. Basically, it's like, so I'll put it in quotes, the H is shared between the two O's. I'll put that in quotes. It's slightly more complicated than that. But, so here's the idea. Any water molecule, these bonds are polar. Because, why? Because hydrogen is not particularly electronegative. Oxygen is. Oxygen's pulling on those electrons big time. So it's a slight negative charge. So water molecules are going to tend to line up like this because unlike charges attract. So it's got a negative charge here. So a nearby water molecule is going to pivot around and send its positive charge to point to that, right? Because the positive charges attract the negative. And other water molecules will line up like this, and water molecules will line up here and down there, and they can form this huge network of hydrogen bonded things. Let me give you a rule for how hydrogen bonds work, and then I'll take questions, because there's sort of a general rule for that, and then I want to apply it. So in Bio 111, in chemistry they're going to tell you it's slightly more complicated, but for us, H bonds can form between the following things. You have to have two partners to make a hydrogen bond. A, what's called a hydrogen donor, that is an H covalently bonded to N or O. And B, what's called a hydrogen acceptor. So the two halves of the bond is a lone pair of electrons on N or O. And as a note, it's never between C8, or never with, I should say. So there's a lot of pieces there. Any bond requires two partners. An ionic bond is easiest to understand. Plus and minus, we attract each other. Opposites attract, okay? Hydrogen bonds are slightly more complicated. What you have is a slight positive attracted to a slight negative. And so it turns out you have to have a hydrogen covalently bonded to a nitrogen or oxygen. That's one half of the possibility of a hydrogen bond. Up there, you can see that. And then the other half is a lone pair. So that's why, those lone pairs are important and why I've been drawing them in. Because those lone pairs can form hydrogen bonds. Right? So the thing to remember, though, that's really important, and it's a mistake that people make a lot of the time, and it's easy to do it, is that hydrogen bonds cannot form with any hydrogen. They have to be, if you like, special hydrogens. That is, hydrogens bonded to an oxygen or a nitrogen. That is, hydrogen stuck on a carbon, they are not special. They are, why is that? Because this bond is not polar. There's no plus minus here, so there's no attraction. Likewise with sulfur and hydrogen, they're the same electronegativity, so there's no polarity. So hydrogen bonds form between a lone pair on an oxygen or a nitrogen and a special hydrogen, only ones attached to N or O. Okay. And that's a thing to be, I'll show you some examples where you have to be careful about that in a second. But questions about that before we do some examples and get to work? Yeah? So if you tried to have H to H? So the question was up there, that's a good one. So up there, what if you had them facing H to H? They would actually repel because each of the H's is positively charged, slightly. So there'd be a slight repulsion. So if you tried to face them H to H, one of them would flip around to face the other way. It's sort of like magnets with north and south, if you like. So this would not be, H to H is not a hydrogen bond because they would actually repel each other. Yeah? So what you got, there's an A and a B. So actually, what I will do, let me draw you a slightly more complicated example, and I'll show you what I can put it up here. In this case, if you want to mark them up, let me do a different color. I can do it on here. It's easy enough. So this guy is the acceptor. That is part B, and this guy is the donor in that case. All right, so that's part A. It's a hydrogen attached to an oxygen, and this is part B below. Right. Okay? So let me show you another, for instance, where we can do those pieces as well. So possible H bonds between H2O and NH3, water and ammonia. So I'm going to draw, actually let me give myself a little more space. So water looks like this, O with its lone pairs, H, and ammonia, H, N, dot, dot, H, H, and then another water molecule, say, O. Okay? And we can make a number of nifty hydrogen bonds, one here and one here. And if I do them in colors, which end is that? That green one there, donor or acceptor?
Acceptor.
Acceptor, right? It's the lone pair. It's part B. It's a lone pair on an oxygen. So that's an acceptor end. So acceptor. And this end here is which? Is the donor, because that's the hydrogen attached to the nitrogen or oxygen. And likewise, this guy is which?
Acceptor.
Acceptor also. Lone pair on an oxygen or a nitrogen. And this is the donor here, right? And actually, I should write that in nicely. These guys are H bonds between a donor. So you can't have a donor-donor. You can't have an acceptor-acceptor. That's the analog of having like a minus and a minus. They won't stick together. And a plus and a plus won't stick together. You have to have a plus and a minus. You have to have a donor and an acceptor. Right? And actually, there's lots more. You dissolve ammonia in water, and there's zillions of hydrogen bonds you can imagine making from all those other hydrogen and lone pairs. Right? Part of the point of this is it doesn't have that you don't have to go from nitrogen to nitrogen or oxygen to oxygen. It can be, you can mix and match. Questions about that? Yeah. So the S minus, those are actually deltas. Those are so what makes this attract is that's delta plus, a small amount positive, and that's delta minus, a small amount negative, because the bonds are polar. All right. Yeah. What about phosphorus? Phosphorus doesn't make hydrogen bonds either, because it's got a medium electronegativity as well.